So we looked at this table, and just very briefly, this table, I would recommend going through it and try to really understand what it means, because it'll give you a better understanding of the gas laws and how they're all interrelated. One of the things that I remembered when I was giving this lecture yesterday to Reedley College is that if you take your PV equals NRT, right, PIV-NRT, remember that for all of our previous gas law equations, we're going from one set of conditions to a new set of conditions. We can actually still do that with PV equals nRT, but we set it up a little bit differently. So we do P1, V1, and then we're actually going to take R and T and move them over here. We'll get, or not R and T, excuse me, N and T, and we'll move those over. N1, T1 equals P2, V2 over N2, T2. So if we set one set of conditions, again, right, an initial pressure, volume, number of moles, and temperature, if we change 3 of those variables, we can predict how the 4th variable will change. And if you look through this table, again, write this out and go through it yourself. If we have V, or volume and pressure changing, but we hold N and T constant, that means going from our condition 1 to our condition 2, number of moles and the temperature doesn't change. So N1 will be equal to N2 and T1 will be equal to T2. So we can remove those from the equation. Because when you do go to inevitably rearrange it, if you leave them in there, they'll cancel out. And so that would give us P1 V1 equals P2 V2, or Boyle's law. So Boyle's law is just a special condition of this version of the ideal gas law, where the number of moles and the temperature are constant. You can do the same thing if you hold other variables constant as well. So if number of moles and pressure are constant, and you have a change in volume or temperature, then P1 will be equal to P2, N1 will be equal to N2. So those will cancel out, and we get V2 over T1 equals, V1 over T1 equals V2 over T2, which is Charles' law. So it's a special set of conditions for this ideal gas law set up this way. So really, you don't have to remember everything. Because if we take this, actually let me copy this, and we'll go back to this problem. We'll just paste this in here. So if you can remember this, and we look at this equation, or this question, we had a, this is actually our ending number of moles. So that's would be our N2. Then we have a starting number of moles, so that's N1. And we had an initial volume, so that's V1. And what we're looking for is V2. Now, this problem doesn't say it explicitly, but the implication here is that P1, or that pressure and temperature, are constant, so they don't change. So those will cancel out and just leave us with what is ultimately Avogadro's law. Just by plugging in the variables you have, you can figure out and kind of derive the simpler gas laws from the ideal gas law. All right. So you can go through that, and you can do these, or you can go back and redo those examples using that ideal gas law, seeing how these things cancel out, and give you the simple gas laws. But let's do an example just using the ideal gas law. So PV equals nRT. And also, these are going to be like the simple gas laws. It's just a matter of figuring out which equation to use and then rearranging it correctly for the variable you're looking for. So we want to calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So we can write all of our variables out, P, V, N. I'll write R here and T. So R is a constant. It will always be the same, right? It'll be constant. So that's automatically 0.0821 atmospheres liter per mole Kelvin. So our pressure is going to be 1.37 atmospheres. Our volume is what we're looking for. We have 0.845 moles of nitrogen. And our temperature is 315 Kelvin. So we can just plug all these in. Times V equals 0.845 moles times 0.0821 atmosphere liter per mole Kelvin times 315 Kelvin. Move this over too. So then we just have to take both sides and divide them by 1.37 atmospheres. And then solve the math on the right side of this equation. You could also do all of the multiplication on the right side and then divide by 1.37. Those steps don't matter what order you do them in. So 0.0821 times 315 divided by 1.37. So volume equals, how many sig figs do we have? Yeah, 3 sig figs. So we're going to be 16.0 liters. And we know that our volume here is in liters because if we zoom in on the gas law here, we have moles divided by, or multiplied by 1 over moles, Kelvin multiplied by 1 over Kelvin, and then atmospheres divided by atmospheres. So liters are the only units left. Cool. A lot of plug, a lot of chug. Again, right, another just ideal gas law problem. One of the key differences between an ideal gas law problem, and I think I mentioned this already, but it's that we're not changing conditions. So we're not told like, oh, the balloon was, this volume at this temperature. What's the new volume at the new temperature? It's just, here's the volume, pressure. What do we have in this one? We want to know the pressure. So we have the volume, we have the number of moles, and we have temperature. So we just need to plug those into the equation. Also need to correctly identify the variables. So what's our pressure? It's unknown. The volume? Whoops. 8.5 liters. Yep. 0.5 liters. Number of moles? 0.55. What's R? 0.0821. Atmosphere, liter per mole Kelvin. And then our temperature? 306 Kelvin. So as a quick initial check, we just want to make sure that all of our units match the units for R. So we have volume in liters. We have number of moles in moles. That one's almost always the same. And we have our temperature in Kelvin. So we'll be solving for this pressure in atmospheres. So we'll have P times 8.5 liters equals 0.55 moles times 0.0821 atmospheres, liters, mole, Kelvin, and then 306 Kelvin. So just to show that we can do it this way, I'm going to do the multiplication on the right side first, and we're going to compress that down or condense it. So 0.55 times 0.0821 times 306. So it's 13.81743. What are the units going to be there after we multiply by number of moles in Kelvin? Atmosphere liters. So atmosphere liters. So it's a compound unit. And on this side, we still have pressure times 8.5 liters. So we divide both sides by 8.5 liters. And we'll get pressure equals that number divided by 8.5. 1.6. We only have two sig figs. Yeah, 8.5 and 0.55. So 1.6 atmospheres. How would we convert that into PSI? Can't just square it. Can't just square it. So PSI, it's 14.7 PSI equals 1 atmosphere. So I'm going to multiply this by, what do I put on the top? What do I put on the bottom? Mm-hmm. And then it's 14.7 PSI on top. Oops. 14.7. They still need to air up their tire. That's only 23 point, well, because of sig figs, 24 PSI. Unless they're racing and they're keeping it flat so that the tire pressure goes up when it heats up. Yeah. Okay. So how much volume does a 0.556 mole of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees C? So what's our pressure? 715 millimeters of mercury. And our volume is unknown. N is 0.556 moles. R is always 0.0821 atmosphere liter per mole Kelvin. Temperature is 58 degrees C. So can we plug the numbers in? What are our units? Celsius is wrong. Yeah. Well, and then millimeters of mercury. So this is a unit conversion you should memorize. It's 1 atmosphere equals 760 millimeters of mercury. So we want 1 atmosphere, or we want atmospheres, I should say, not 1 atmosphere. And that's 760 millimeters of mercury. So we take 715 divided by 760. 9407 dot dot dot. We want the rest of those. Want to keep the rest of those in there. Then 58 plus 273.15. 331.15 Kelvin. All right, now we got things in the right units. We can plug these in. So it'll be 0.9407 atmospheres, times volume equals 0.556 moles times 0.0821 atmosphere liter per mole Kelvin, times the temperature, 331.15 Kelvin. You think I'd eventually learn to write farther over instead of running out of space every time?
You wouldn't write it as 941?
No, because we don't want to round it yet. We want to use the whole number for our calculations and then only round the reported answer. So if you wanted to keep track of the fact, though, that there are only 3 sig figs, I usually just underline the 3 sig figs. All right, I'm going to multiply the right side again. 0.556 times 0.0821 times 331.15. So we're going to get 0.9407, again, only 3 sig figs. Atmospheres times the volume, and that'll give us 15.116. And then again, we're multiplying by moles and Kelvin, so our units here are going to be atmosphere liters. And that should only retain 3 sig figs. So we can divide both sides by 0.9407. Atmospheres. So that atmospheres will cancel out. And volume will be 16.1 liters. Yeah, so most of this work will come from identifying what equation to use, plugging the numbers in, and then doing the algebra correctly. Yeah. So as I mentioned before, though, we can use the ideal gas law with mass measurements to calculate the molar mass of a gas. One of the ways you can do this is if you have a container, usually a rigid container. This is how I got these scars. My professor in undergrad did some glass blowing, and actually took a glass blowing class with him, which is really cool. But he made these round bottom flasks, and then he took like a glass burette thing and fused it onto the top. And so we connected that up to a vacuum pump, pulled a vacuum so it sucks all the air out, filled it up with pressurized oxygen. I think we did oxygen, nitrogen. I feel like we did, probably helium. And so what you would do is you do that a few times. So kind of flush it out so that there's only oxygen gas or only nitrogen gas inside the flask. And then we knew what the mass of these things was. They were like, like 170 grams or something. And so the mass then, when you put that on the scale, would be the mass of the gas inside. But while I was holding one, filling it up, I was holding it like right here, it exploded. And it was like a shotgun going off the room, and it launched several pieces of glass into my arm. Fortunately, nowhere else. And then I didn't get any cuts on my hand, but I had some cuts on my stomach from the glass going through my shirt. So wear safety goggles, especially when you're working with pressurized stuff. But you can do that experiment. I don't think we're doing it in, not this exact experiment. There's a much safer experiment you can do, but this was PChem. So if we have a sample of gas that has a mass, and so we have to be given the mass, its volume is 224 milliliters at a temperature of 55 degrees C and a pressure of 886 torr. Find the molar mass of the gas. So we've been given a lot of units here that we need to convert. So pressure, volume, N, R, T. So our pressure is 886 torr. So this is where memorizing all these, there's a lot of different units of pressure. Just got to memorize them. Our volume is 224 milliliters. N, and N here is not explicitly stated, right? It doesn't explicitly say we need to find the number of moles. So this question is relying on you to know that molar mass requires N because it's moles divided, or sorry, is grams per mole. Grams per mole. So we've been given grams. If we can find moles, then we can take our grams, divide by moles, and get the molar mass. And in some cases, identify the gas. Okay, so we have our pressure. Moles is what we're looking for. It's kind of left to you to infer that. A little critical thinking. R is still going to be 0.0821 atmosphere liter per mole Kelvin. And our temperature is going to be 55 degrees C. Yeah, so there's several things we need to convert here. Because the units that we have to match are those of R. So if R is atmosphere liter per mole Kelvin, then we need to be plugging those units in to be able to solve it. So torr is actually equal to millimeters of mercury. Let me write it like this, actually. So 760 torr is 760 millimeters of mercury is equal to 1 atmosphere. So we can kind of do double duty in terms of the conversion factor. 760 is an important number. So to convert torr into atmospheres, we have to multiply by 1 atmosphere over 760 torr. I guess we'll just do that right now. 886 divided by 760 will give us 1.1657. Yeah, because I'm not going to round this yet. Atmospheres. That's 3 sig figs. How do we convert milliliters into liters? Thousand milliliters in a liter, yeah. So if we want liters, then we're going to put liters on top. This is getting really congested here. We do this. So we'll divide by 1,000 milliliters. Or you can take the decimal place and move it over 3 places to the left. So this will be 0.224 liters. R, of course, is constant. And our temperature will add 273.15 to get Kelvin. So that'll be 328.15. Okay, now we've got everything sorted out. We've got all the right units. We can solve for moles. I'm going to do this a little faster here. So we're going to have 1.1657 atmospheres times 0.224 liters equals N is what we're looking for, times R, which is 0.0821 times 328.15. Algebra magic happens. Times 320. So I'm doing the R, 0.0821 times 328.15. Then I'm going to divide by the 1.1657, and then divide by 0.224. That doesn't feel right. That doesn't feel right. I got 103. How many sig figs? We got 3 sig figs. 103 moles. That definitely feels wrong.
Because you multiply R by the temperature and then divide by that number, so there's moles left, or no?
So yeah, because this is, so we have moles, and then R is going to be, so we're going to multiply by Kelvin, and then we actually divide this over to the other side so the thing flips, and then we get atmospheres and liters canceling. Yeah, which would leave us with moles. That's a lot of moles. We can do this. 'Cause I feel like that number was smaller when I did it yesterday. Right there it is. Yeah. What did I type into my calculator wrong? Did anybody else do this math? What did you get?
I got the 0.009.
That's what I got.
9,200.
I got the same thing.
Oh,
What I did is I times the 0.081 times 328.
I did it backwards.
And then divided it both sides.
Yeah, 103 is 1 over the correct answer. Yeah, okay. Try to do it fast. See, this is why you don't try to go fast. I always remember that line from one of the Bourne movies. Slow is smooth and smooth is fast. That's honestly the key to doing this kind of thing. If you go too fast, you make mistakes. Okay, so now we have moles, we have milligrams. Converting milligrams to grams is the same as milliliters to liters. So we can move that decimal place over 3 spots to the left. So it's going to be 0.0388 grams divided by 0.00969 moles. So 0.0338 grams divided by 0.00969 gives us 4.00 grams per mole as our molar mass. So what element do you think this is?
Helium.
Yeah. Oh, I get to use this. Helium. So bright that you can't even see it. Yeah, green laser pointers, very impractical for actually pointing at things, unless you're pointing at stars, and then you can see the beam of the laser pointer through the air. It's also why you should never point them at airplanes. because you can actually hit the airplane. Okay, so we've got another sample of gas weighing in at 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees C, pressure of 976 millimeters of mercury. Find its molar mass. So let's write all these in. Should be noting there's a whole lot of repetition to these. Our pressure, 976 millimeters of mercury. Volume is 0.270 liters. Number of moles is what we're looking for. R is 0.0821 atmosphere liter per mole Kelvin, and then 88. All right, 88 degrees C. So here we'll take millimeters of mercury. We'll divide that by 760 to give us atmospheres. And we'll add 273.15 to degrees C to get Kelvin. And why do we need to do these things? Because of what? Sorry, I just didn't understand which. Oh. For degree C, yeah. So you never end up with 0. Yeah. That is one reason.
You have to match it up with R, right?
Yeah, that's kind of more what I was looking for, but, potato. Yeah, so the units have to match with R. Specifically for degree C, you never want to end up with a situation where you divide by 0. So this is going to be your atmospheres. And then 88 plus 273.15 is 361.15 Kelvin. So if PV equals nRT, we can plug these numbers in. So atmospheres times 0.270 liters. We're looking for N. That's our R value. And our temperature will be 361.15 Kelvin. So we'll do 1.28. Actually, I have the exact number. 1.28 times 0.270 divided by 0.0821 divided by 361.15. So we'll get 0.0117 moles equals N. Okay, so now how do we calculate the molar mass? Grams over moles, yes. But we have milligrams. So I'll do this over here. So if we have 827 milligrams, our decimal place is here. If we want to go to grams, we just move that over 1, 2, 3. So that'll be 0.827 grams. 0.827 grams divided by our new number of moles. .827 divided by that number gives us 70.7 grams per mole. Any guesses for what gas this would be? So gallium's close to 70. So if we had boiled gallium, the temperature's not super hot here. I don't know what temperature gallium boils at. I think it's actually chlorine. Because chlorine is going to be Cl2. So 35.45 times 2,
Oh, yeah, it's like 70.
70.7. It's close enough. Yeah, so this is probably Cl2. That doesn't always work, but if you don't know anything else, it can give you an idea. Cool. So up till now, we've only been talking about ideal gases, which obviously is not going to be all gases. Typically, the ideal gas or ideal gases become non-ideal gases when you start moving to extremes. So in our ideal gas conditions, we have high temperatures, low pressures, meaning that we have particles moving very fast and not very many particles. Then our particle size can be small compared to the space between particles, and interactions are insignificant. But, and actually I'll switch over to this. So you can imagine that this is our ideal gas, right? Relatively low pressure. I mean, it's kind of high actually, but it's 300 Kelvin. We'll cool this down a little bit. So we've got all these particles in here, and they're bouncing around having a good time. But if I start just like stacking particles in here, now all of a sudden they're not so spread out, and they're actually pretty close to each other. And when they get packed in like this, they do start to interact. They can start to stick to each other. Most cases, they'll start to become liquids if your pressure gets too high. And if you take more advanced chemistry, there are equations for accounting for the fact that they're actually a little bit sticky if they're too close together, or if temperatures get too cold. What was the other one? They start to stick together, and sometimes they don't travel fast enough to be a gas anymore. But we don't cover those. Just know that everything we're doing is for ideal gases. Okay. So this would be applicable to the lab that we did last week. We're starting to get into this a little bit. According to kinetic molecular theory, each of the components in a gas mixture acts independently of the others. So if you have nitrogen and oxygen in a container together, right, the particles aren't interacting. So it doesn't matter what the particles inside actually are. Especially on this guy, we can take out a bunch of these light particles. So we got most of them. So we can throw heavy particles in here too. The heavier particles move slower, especially if the temperature is a little cold. But they're not really interacting in any special way with the light particles. Right? We could have a medium particle, an even lighter particle. Doesn't matter. The pressure, though, of each component in that mixture is actually related to how much of that component there is. So actually, I think this is the better demonstration here. So here we're at 11.1 atmospheres. If I take out all of our heavy particles, so we've only got light, we drop to 5.8. I can add 50 more light particles, or 11.6. Why did I go to 12.6? Out of the chimp. Something a little weird going on with the with it there, but all right. So it doesn't really matter what type of particle we have. The amount of particles related to the or the pressure of the particle is its partial pressure of each type of component. This sentence is a little densely worded. So the partial pressure of any component that is that component's fractional composition times the total pressure of the mixture. So I'll give you an example here. Go back to this real quick. So let's say that the light particles are oxygen, the heavy ones are nitrogen. So we've got 50% one, 50% of the other. So our pressure here is 15 atmospheres. Let's go back over here. So we could plug in here, total pressure, 15 atmospheres, times the fractional composition of the particle. So here we're 50-50. So let's just do oxygen. So the fractional composition will be 0.5. I'll do oxygen. And that will equal the partial pressure of oxygen. So in this case, it's just half. So 7.5 atmospheres of the total pressure are coming from oxygen. And we can get, of course, more granular than that. So our atmosphere is made up of these, or this mixture of nitrogen, oxygen, argon, carbon dioxide, and then some other ones, like helium. So nitrogen molecules in air exert a certain pressure, and that's 78% of the total pressure. So at sea level, that should be, let's use 760 because it's a little more interesting than 1. So if we have 760 torr at sea level, the pressure contributed by nitrogen, we'll take 760 times 0.78. That's its fractional percentage for N2. $760 times 0.78 be 592, 0.8 torr. So at sea level, 592.8 torr is coming just from nitrogen gas. So if you removed all the nitrogen gas, you would remove that much pressure. And then oxygen molecules are exerting 21% of the total pressure. So, right, glass is half full. If you're an optimist, it's half empty. If you're a pessimist, if you're a chemist, it's 50% water, 39% nitrogen, 10.5% oxygen, 0.44% argon, and 0.06% CO2. Because, of course, it's full unless it's somehow in space with water, even then. So the fractional composition, and you might remember this going back to calculating the atomic masses that we see on the periodic table. We have to use the fractional composition, meaning the percentage divided by 100. So here if we have helium is 80%. So let me do it like this. The percent helium is 80%. The fractional composition equals 80 divided by 100, or 0.8. So just remember, for these partial pressures, we've got to be using the fractional composition, not percents. Okay, so if we have a gas mixture containing 64% methane, 36% ethane, if the pressure is the total pressure, so I'll abbreviate total pressure as P sub T. So total pressure is 1.44 atmospheres. What are the partial pressures of each component? So we'll take our total pressure of 1.44 atmospheres and multiply by the fractional composition of each. So it'll be 64% divided by 100. So 1.44 times 64 divided by 100 will give us 0.92, 922. What units are our partial pressure going to be in? What was that? Liters? They'll stay the same as whatever our total pressure is. So fractions, and actually percents only kind of have a unit. just to tell us that it's been the fractional composition multiplied by 100. But this is essentially unitless. So if we have our total pressure in atmospheres, then our partial pressure will also be in atmospheres. A little bit, yeah. A little bit of a trick question. So then for ethane, let me write this out. This is methane. We'll again take our 1.44 atmospheres and multiply by 36% over 100. So 1.44 times 0.36 will give us 0.51. Oh, I guess we only have two sig figs, huh? 5.2. So it should be 9.2 and 5.2? Yeah. And again, we keep the same units as our total pressure. So this is ethane. Can anybody see another way that we could have calculated ethane, the partial pressure of ethane, if we had already calculated the partial pressure of methane? Yeah. Yeah, right? So if we know the composition of everything except for one of our partial pressures, then we can just subtract out all the ones we know from the total pressure and get whatever that last one is. So in this case, we only have two things. So if we know one, we can just take the total pressure minus the partial pressure to get the pressure of one of the components, which is Dalton's law of partial pressures. So the sum of the partial pressures of each component has to equal the total. Oh, TOT is total pressure. So in that previous question, our P total would have equaled the partial pressure of ethane plus the partial pressure of methane. So P sub A would be, component A, component B, component C. You can have as few as one and as many as, I guess, an infinite number of components. Aha. So this is essentially what you guys did last week. If you have a sample of hydrogen gas mixed with water vapor, so you have hydrogen gas and water vapor, the mixture has a total pressure of 745 torr. And the water vapor has a partial pressure of 24 torr. Should we do it this way? P tot is 745. And then P water has 24 torr. What is the partial pressure of the hydrogen gas? Actually, don't have to convert. No, yeah. So we don't have to convert unless the question asks for it in different units. Yeah, these ones, everything has to be in the same units. Yeah, so you just subtract it. So if 745s are P total, we just subtract out the vapor pressure of the water vapor to get 721 torr. And then, if you were asked to, you could convert it from there. So this is what you had to do with the lab last week, is you had to subtract out the vapor pressure of that water, because that would affect how much hydrogen gas you calculated. So lungs perform best when the oxygen partial pressure is 0.21 atmospheres, because that's what our atmosphere is. At higher elevations, that drops, and so does, the total pressure drops. And so then the partial pressure of oxygen also drops, which can lead to hypoxia, so not getting enough oxygen. You can also get oxygen toxicity if the oxygen levels go too high. So you don't want to give somebody high flow oxygen unless they actually need it. Although that does make me wonder, have you guys seen those oxygen bars? Where you just like go there and you like breathe scented or flavored oxygen? I've always wanted to do that. They're not super popular though. Right? It's like, all right. And then, you know, I would of course ask them like, okay, so what's the pressure of the oxygen that you're giving me? I need to know if this partial pressure is too high. So you get oxygen toxicity if the partial pressure of oxygen goes above 1.4 atmospheres. You have muscle twitching, tunnel vision, convulsions may occur when breathing pressurized air, such as while scuba diving. So that's why you need the pressure regulator to be giving you constantly 1 atmosphere of overall pressure. But if you get to higher and higher pressures, you start to dissolve more nitrogen into your blood, which is called rapture of the deep, and apparently feels similar to being tipsy. So instead, you use heliox, which is a mixture of helium and oxygen, instead of nitrogen. That's why deep sea divers always sound funny, because they're essentially breathing nitrogen, so their voices are all high pitch. Which, fun fact, so if breathing helium makes your voice higher pitch, breathing argon or krypton or xenon, or one of the ones that people will use is sulfur hexafluoride, the heavier the gas, the lower it makes your voice. And it also distorts it, makes it sound really weird.
Have you tried these?
No, but I just saw a TikTok last night.
Are you trying these at home?
No, I wish. It definitely would. So sulfur hexafluoride is pretty stable, but the noble gases definitely are stable. Although you don't want to breathe straight radon because it's radioactive gas. That has different problems. Okay, so a diver, get distracted by the fact. Like, of course I'm getting like super, whatever, TikToks, right? TikTok figures you out and sends you stuff that it knows you're going to like. Guy breathing all the different noble gases. It's pretty good. So if a diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure, or he wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres, what must the total pressure be? So he has his oxygen composition is 5%. Is there information missing here? This is not one that I immediately remember how to solve. So let's figure it out. All right, so if we got 5% oxygen, this will actually be a good example. This is how I solve problems. So if we got 5% oxygen, let's just assume that he's at 1 atmosphere. So his pressure total is 1 atmosphere. Oh, wait, no, I know what this problem is now. Yes. Okay. Nope, I remember how to solve this. So remember, Dalton's law of partial pressures is pressure total equals PA plus PB plus PC, ... The other law that we learned for partial pressures, and this one, first of all, why can't we use this?
You're only given one, right? Or the total is being adjusted, so you can't use it, something like that?
Yeah, or the total's being adjusted, but we're also using, I guess if we assume that the rest is helium, so we've got 95% helium, 5% O2. We don't know what the P total is, so I guess you could plug in here, just assume 1 atmosphere, and say that this is now 0.95 atmospheres helium plus 0.05 atmospheres oxygen. You could kind of do some guesswork there. I think the easier way, though, is the other one that we learned is that pressure total is equal to the fractional composition times the fractional composition times the, okay, froze on me. It's the total pressure. So I did it backwards. Yeah, so fractional, yes. The partial pressure of O2 is equal to the fractional composition times pressure total. So now we have the fractional composition. We have the total pressure, or sorry, the partial pressure, so we can solve for P total. So partial pressure of oxygen, which is what we want, is 0.21 atmospheres. Our fractional composition is 0.05. Right, so 5% divided by 100. It's actually 50. That multiplied by pressure total has to equal 0.21. So then we can take 0.21 divided by 0.50. So we got 4.2 atmospheres equals the total pressure. So yeah. If you can figure out the equation where you have all of the variables except one, it's probably the one you're supposed to use. The only exception is sometimes there are sort of hidden variables, like solving for molar mass. Okay, so when a gas is collected through water, water molecules become mixed with the gas molecules, and the pressure of the water vapor in the final mixture is the vapor pressure of water, which depends on the temperature at which the gas is collected. So this is where you guys did this experiment almost exactly. Had like an intermediate thing. But we took the zinc, dissolved in HCl, hydrogen gas came out, went into the big flask, which pushed water over so that you could collect or calculate the volume. But in that space above even the zinc and HCl solution, there's going to be some amount of water vapor. So if hydrogen gas is collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees C, what is the partial pressure of hydrogen gas?
It's 758 minus 23.8.
Yeah, so we can just look up this value. I used a calculator to try and give you guys more accurate numbers. But we're at 25 degrees C, so we can say 25 degrees C. Our partial pressure is 23.8. So we take our 758 minus 23.8. So 34.2. So this is just a rearrangement of, again, Dalton's law of partial pressures. P total equals pressure, in this case, of hydrogen plus the pressure of H2O. So we know the pressure of H2O from the table, and we were given the total pressure. Cool. Oh, yes. Gases and chemical reactions. I told you that everything builds and everything stays important. So in reactions involving gaseous reactants or products, the amount of gas is often specified in terms of the volume at a given temperature and pressure, right? Because if we have temperature, volume, and pressure, we can calculate the number of moles. And it's a lot easier to get those three things than it is to try and get like the mass of the gas. As I explained before, that can be dangerous. So use the ideal gas law to convert pressure, volume, and temperature into moles. So we can just rearrange this to solve for moles. So we'll get PV over RT equals N. And then you can use stoichiometric coefficients to convert to other quantities in the reaction. So like the magnesium, I think we use magnesium, right? Magnesium plus HCl to get H2 plus MgCl2. I could give you a pressure, volume, and temperature of the hydrogen gas that you collected. And you could calculate the number of moles. And then you could use that to figure out how much magnesium you had started with, or how much of the hydrochloric acid you reacted with to form that much hydrogen. And it's less useful, but how much magnesium chloride was also produced. So in this reaction, 4.58 liters of O2 were formed at 745 millimeters of mercury, 308 Kelvin. How many grams of silver oxide decomposed? So we had silver oxide in some sort of solution, or silver oxide solid, decomposing into silver metal, oxygen gas. So let's start just by writing these out. All right, so we have a pressure that's 745 millimeters of mercury. Volume equals 4.58 liters of O2. Temperature is 308 Kelvin. And what we want to know is the grams, well, how many grams of Ag2O? So where can we start in this reaction, or in this question?
We need to convert, or no,
Convert what?
745, no, right? There's nothing that's converted to atmosphere, or doesn't matter?
Why do you want to convert it into atmospheres? It's a good guess. Okay, so if we want to get to, and maybe we can work this backwards. So, been a while since we did one of these, but let's do a solution diagram. But we're going to start at the end. So we want grams of Ag2O. We're kind of working back in the direction of the oxygen, because that's the only thing that we know anything about. So if we wanted to get from grams of, I'm going to draw this arrow backwards here. If we're trying to get to oxygen, what will we do?
Gotta find the molar mass.
You do the molar mass, right? And find the number of moles of silver. Silver oxide, so moles of silver oxide. Okay. So how would we get moles of silver oxide, or how could we go from moles of silver oxide to We're trying to get closer to oxygen, right? Molar ratio, ring a bell? So if we knew the moles of silver oxide, we use the mole ratio of silver to oxygen to calculate the moles of oxygen. Okay, so if we got the moles of oxygen, then we could solve this problem. So how do we get moles of oxygen? Grams of oxygen, molar mass would be useful, but we don't have the grams of oxygen. What equations do we have? Which gas law equations have moles? Ideal gas law. Okay. So without going and getting any others, so if we had pressure, volume, R, which is a constant, and temperature, then we can find the number of moles. So we have pressure, we have volume, and we have temperature. So, and R is a constant, 0.0821 atmosphere liter per mole Kelvin. So you're right, we do need to calculate this, convert this into atmospheres divided by 760. But I did want to get to the Y. Yeah, I wanted to get to the Y. 0.980 atmospheres, let's call it. Okay, so we're going to use PV equals nRT to calculate moles. Just rearranging this up front, it'll be PV over RT equals N. So that's 745. 0.980 times 4.58, what's atmospheres, liters, over 0.0821. And then times our temperature, which is 308 Kelvin. So 0.98 times 4.58 divided by 0.0821 divided by 308 means we have 0.1775 moles of O2. Cool. Now what? Plug it in? Plug it into what? Right. So yeah, we got to here. So how do we get from moles of oxygen to moles of silver oxide? The ratio, E. It's 2 to 1. And actually, maybe I should write it out like this, because now we're doing stoichiometry. Could not use an eraser, though. That'd be cool. Yeah, 2 to 1. So 1 mole of oxygen. That'll go in the denominator. Will be 2 moles of Ag2O. And then that'll give us moles of silver oxide. How do we get to grams of silver oxide? Molar mass, yes. So silver is 107.8682 times 2 plus 16. So this is, remember molar mass, it's been a while now, but molar mass is grams per mole. And the mole is always 1. always 1 mole, and the mass is always a larger number. So this will be 231.7664 grams of Ag2O 1 mole. So we can take 177.5 times 2 times 231.7664, and we'll get that. We decomposed 82 sig figs or 3 sig figs, 82.3 grams of silver oxide. This is kind of why I didn't want to do chapter 11 with 9 and 10, because there's a lot of in chapter 11, and it's very different from 9 and 10. Cool. Well, I think there's another example. Oh, yeah. You got to get into this. All right, so are there any questions about that, these kind of problems? These are like A-level questions, because now we're taking something from chapter 11 and something from chapter 8, as well as, like 5, 6, and 7, and mashing those all together. So you got to really start bringing these previously unrelated topics, unrelated in that we never talked about them together, and bring those puzzle pieces together. So standard temperature and pressure is a very useful thing. And it comes from scientists wanting to not use PV equals nRT all the time. So they said, okay, we're going to have this universal standard, and standard temperature and pressure is a temperature and pressure that are constant. So it's always going to be 0 degrees C and 1 atmosphere. Or in this case, 273 Kelvin. All right, so let's calculate then. If we're at STP, standard temperature and pressure, what is the volume of 1 mole of gas? So pressure, volume, nRT. So if we solve this for volume, right, nRT over P. So this is going to be V equals 1 mole times 0.0821 atmosphere liter per mole Kelvin times our temperature, which is 273 Kelvin, and then 1 atmosphere in the denominator. So we'll have 0.0821 times 273. So the volume of 1 mole of gas at STP is always 22.4 liters. So that's where molar volume comes in. So molar volume, like molar mass, is liters per mole. And it's even easier than that, because for every gas, it's 22.4 liters per mole, as long as you're at STP. So if the temperature is 0 degrees C, the pressure is 1 atmosphere. As soon as you deviate from that at all, it's different. Yeah. So definitely, if we go back to a problem like this, where there was a lot of work that we had to do here, we had to do the whole PV equals nRT thing, I will definitely give you a problem where you don't have to do this, because I'll say this is at STP. So all you'll have to do is go from the volume to the number of moles using molar volume. Just letting you know. So this works out because it's just the number of particles in that space at STP. The mass can be different, but the volume is the same. Because it's the same number of particles, the mass doesn't actually matter. All right, this is the last question here. So how many liters of oxygen in STP are required to form 10.5 grams of water? I know, it's 6:31. Where should we start with this problem?
You're gonna write them out, right?
Got to write them out?
Identify.
It's a STP though, so you'll just use
Oh, that's right.
It's at STP, so that's nice. But we have only 10.5 grams of hydrogen, or of water. That's the only number we're given. We want to know how many liters of oxygen. So we're trying to go from here to here. If we want to convert from one compound or element in a chemical equation, we always have to do so through moles. Every time. There's a question that says, how many liters of oxygen to form water? You're going through this, at some point you have to go through moles. So how do we get from grams of water to moles of water?
You do 1 gram at the bottom of water. You go from there, no?
1 gram?
Or
Molar mass. The murmur molar mass. So the molar mass will get us, because 18.02 grams per mole for water. So we'll put 18.02 in the denominator, and then 1 mole H2O. Because our molar volume is only for gases. Although I guess this is gaseous water. Okay, now what? Molar ratio. So we want moles of oxygen. So there's 1 mole of oxygen, 2 moles of H2O. Now, how do we calculate liters of oxygen at STP from moles of oxygen? 22.4 liters per 1 mole. So 10.5 times 22.4 divided by 18.02 divided by 2 gives us 6.53 liters of O2. Very good. Let me just take a look at the beginning of this. Man. All right, let's take a short break, and then we should start chapter 12. Like Tuesday, we got to go a little long.